Hi everyone, welcome to the 26th edition of the World Energy Markets Observatory. My name is James Forrest. I'm the Global Industry Leader for Energy Transition and Utilities at Capgemini. I'm joined today by Colette Lewiner and Pete King. As you can see, we've done things a bit differently this year. We've recorded 4 discrete chapters of our report. We really hope you enjoyed the first 2. This is the 3rd one on our recommendations on how to reach net zero. We look forward to your feedback.
So there's a really important connection between GDP and energy consumption. So we saw last year that world GDP rose at 3.2%. So to put that in mind, 3% GDP growth means that the world economy doubles every 25 years. So that means by 2050, there will be twice as many schools, twice as many hospitals, twice as many cars. A 2% growth in energy means that energy use will double in 35 years. So that means there'll be twice as much energy use by 2060 if we carry on at the current rate. Which is why it's really important that we decouple economic growth from energy demand. And the story about that is not uniform around the world. And I think actually if we look here in Europe, we can see some really good progress and some learning for others to follow. So Europe has taken a lead because it's made obligations on industries and people. It's done some work, maybe some more needed, on consumer awareness and participation. But also it's benefited perhaps because the price of energy has been so high that people have been much more conscious about reducing their own energy use. So the question here is, will others follow? And that's a critical question as we see the increasing rise of the middle classes around the world. When we look at what this means for individual technologies and how the pathways to the technology development is going, we're seeing a story where it's really not sufficient at the moment. So last year in wind, we added 115 gigawatts where we actually needed to add 500. Solar, we added 350, we needed to add 600. Nuclear, over the next few years, we need to grow our nuclear fleet from 400 gigawatts today to 1,200 gigawatts in future. Green hydrogen is tiny in comparison to what the projected needs are. The storage, particularly by batteries, remains very small. EVs is really promising, but at the moment, the EV penetration into the world vehicle fleet is still very small. Heat pumps, not yet going fast enough. Carbon capture is not yet capable of meeting more than 10% of what we need. And all of these put together will reduce the energy intensity, i.e. the relationship between GDP and energy growth. The unfortunate outcome of this is that the world is on the road to at least 2.7 degrees temperature rise by the end of the century. That means in our children's lifetime, they will see dramatic changes due to climate change. What we're saying we need a far greater focus on the short term. So far greater focus on 2030 as an outcome. We should take rapid steps to reduce and eliminate methane production and methane leakage into the atmosphere. All the developing countries will need help. And unfortunately, we're going to need some adaptation measures. And particularly in the energy sector, we're going to have to take actions to produce and protect our energy sources.
So we looked at what we need to do from now to 2030. Now let's look at from 2030 to 2040, and this would be some disruptive technologies that have to also get into the game. We have selected a few of them: AMO, advanced modular reactors, native hydrogen, space-based solar, superconductivity, nuclear fission, industrial heat, and AI and Gen AI impact. On the superconductivity side, just to remind that there is around 7% electricity lost on the grids because of heating. And when the cable becomes superconducting, it means it is transmitting electricity with no heat. This happens physically at very, very low temperatures, not far from the absolute 0 degree, minus 273. There was in 1986 a big discovery enabling to find materials that were superconducting only at minus 200 degrees, which is the nitrogen temperature. Since then, there has been little progress. Now, superconductivity cables are already used, but in a very limited way, and also superconductivity is used in medicine instruments. The question is, will there be further progress on that, or will we stay there? The fundamental physics is not yet totally understood, so probably it's going to take time. Now, space-based solar, this is an idea. You have much more sun in the space. You don't have nights, it's only days. And the intensity of the sun is much bigger in the space. So the idea is to send satellites and then to put solar panels on them. That can cost money, but it is feasible. The difficulty today is how to repatriate this electricity on Earth. It would be done with microwaves, but the problem is that the waves are spreading more and more as the distance increases, so you would need very, very large installation, few square kilometers installation antennas on the Earth to capture that electricity. But still could be looked at. Now, if we look at native hydrogen or white hydrogen, this could be something that could develop. It is found, hydrogen is found under the Earth's surface. The first one was found in Mali many years ago in Africa. Today there are permits a little bit everywhere, in Australia, in the UK, other continents, to look if there could be white hydrogen, because the projected cost of white hydrogen is very low compared to the green hydrogen. So the question is today, science and geoscience not enough developed to understand where to look for that and to know if it's just a reservoir or if there is a flux of white hydrogen that comes into the reservoir. And now an additional positive point is helium is usually found as a co-product, and this is improving the profitability of those implantations. Another one, which is totally different, is advanced modular reactors. We said before that SMRs are using the same water-cooled technology as today, while advanced modular reactors are using other processes. Those processes were developed in national laboratories in the US, also in France and in Russia probably, but they stayed at the stage of prototypes usually. The question is how to re-enhance that, revisit that, and there are 6 selected nuclear technology that have been selected, and some of them could be of interest. For example, if you look at molten salt technology, it doesn't need water to cool, so could be able to put those reactors a little bit everywhere on the world. Again, fast neutrons reactors also will, of course, better use uranium. So I think something promising will come from that. There are many startups, many billionaires like Bill Gates are investing in that. So there is a future, I think, in that. Now, one topic which is very much popular in the media is nuclear fusion. Fusion reactors are the fact of getting energy if you have 2 atoms that are fusing, and then this is deuterium and tritium, which are 2 isotopes of the hydrogen. So you need a confinement. You need to push those atoms very near from each other. You have 2 ways of doing that. Plasma confinement, you can do it through tokamaks, which is magnetic confinements, or you can have an inertial confinement done with lasers. The first one has all countries in the world have put a lot of money on that one, and there is a huge project, ITER, in the south of France. Unfortunately, they announced recently a big delay and overcost, and they believe that the first plasma will be in 2035, not a given for. So more hope is around inertial fusion, inertial confinement, because in 2022, in a US lab, Lawrence Livermore, they found that they were nearly break even in laser confinement. Nevertheless, there is a lot of work to do, and the route will be quite long from now to get something which is industrial. And so I don't believe that we will have fusion reactors in 2040, perhaps in 2050. We shall see.
Thank you, Colette. We're now going to look at two further technologies, electrification of heat and Gen AI. Industrial heat is a big area of decarbonisation, and there's been reasonable progress. If we look at 200 degrees C, heat pumps are now very credible in that domain. If you look at 400 to 1,000 degrees C, induction and heat and resistance technologies exist, but there's now a trade-off between them and the gas that needs further development. Between 1,000 and 2,000 degrees, there are technologies that exist, typically microwave and infrared, but they still need to be commercially developed for industrial heat. So our conclusion on this is that electrification of industrial heat just needs more commercial development, but it's progressed massively. So now the next topic, Gen AI, the hot topic. As you can see on the graph there, data centers account for 2% of electricity consumption, and it's expected to double in 4 years, according to the IEA. What can we do about that? Well, the first point is large language models are very heavy and they need to be tailored to reduce consumption. And the good news is there are a number of technologies that are moving towards that. Also, rapidly advancing hardware has a big role in terms of reducing energy consumption, and there's been good progress on that. We've seen a rash of announcements also on the decentralization of compute power and siting data centers near demand, and that's been happening a lot. Finally, AI can have a massive impact on reducing energy consumption in 3 areas. Firstly, it can optimize data usage in the data centers. Secondly, it can optimize waste heat. And finally, it can optimize large loads, e.g. EVs. Our conclusion of this third chapter is that we need to accelerate the energy transition. By 2030, we need to accelerate wind and solar, and we need to accelerate storage and use AI as well. In particular, we need to take more advantage of public and private funding. We need appropriate and stable regulations. We need consumer engagement. We need demand-side flexibility. We also need serious political commitment married with good policy, and we need to prepare our youngsters for the new low-carbon jobs. In addition, as Colette has talked about, we need to extend our existing nuclear fleet. We need to stop methane emissions by 2030, and we need to move to a new method of measurement, final energy demand measurement rather than primary energy consumption. We also, at the same time, need to acknowledge that a lot of adaptation measures are needed. Thank you, Colette. Thank you, Pete. Please do look at our final chapter, which brings together all of the recommendations and conclusions.